got the tremendous pleasure and honor of introducing a dear friend, not a very good skier, Chris Schumacher. We met at a conference in Florida 30 years ago, and Chris is now a building science consultant with RDH, and he's now working out of Ontario, Canada. Okay. He's a professor at the University of Waterloo, which is, I think, a pretty reasonable school. They're a big, what shall I say, competitor to my school at the University of Toronto. So they're always picking on us and we're always picking on them. But when the brown organic material hits the fan, we always work together. So please give Chris a warm welcome.
Thank you, Joe. Thank you all. Eva, I don't know what you and I did to piss off Joe, but first slot in the morning after the party or the last slot in the afternoon before the next party. So yeah, as Joe said, we've known each other for about 30 years. He and I have been skiing together for 25. He likes to tease me that I can't ski, but on the left here, this is me last year. I can ski. I'm maybe not as fast and as graceful as I used to be. Joe would probably say that I was never that fast, and I would say he was never that graceful. On the right there, that's not Joe, that's my brother. My brother's a year younger than me. Being so close in age, we grew up pretty tight, close friends. But we're not really a lot alike. You can see there, I've got skis on, he's got a snowboard on. This is what I think of snowboards. So anyway, Joe is asking me, he said, what do you think that people need to hear about? And I said, well, you know, I could talk about mass timber or I could talk about masonry. How much time do I have? I'll give you an hour. Don't have time to talk about masonry. Mass timber is kind of important. So we're going to come back to my brother in a little bit, but this is a topic that I think is becoming important in our work, RDH. We participated in either the construction or the diagnosis of over 50 mass timber buildings. In my mind, there's a higher percentage of those buildings that have problems than there should be. And so I'm trying to figure out what the patterns are. And I think that, as Eva said this morning, context matters. And so as an industry, we're basing our actions on what we understand to be the situation, what we understand to be the physics, and what we know from our experience. And many in the industry don't have a complete picture of that because this is a fairly new approach to building. How many people here have worked on a mass timber building? Okay, that's a good number. How many people here have admired a mass timber building? Okay, how many architects are here? How many of you think that mass timber buildings are sexy? Okay, so see how the majority of the people who raised their hand for architect also said they were sexy? Anyways, so brief background. In 2018, one of my colleagues, Graham Finch, was here. This was 2 years BC, before COVID. Graham presented a session called Mass Timber and Tall Wood Buildings. I don't have enough time to give you a whole backgrounder in mass timber, so for those of you that aren't so familiar with it, you're going to get a crash course here in like 8 slides. If you want more, then I've left Graham's link there. But why mass timber? Well, you know, many people think that they're sexy. We talk about the fact that they've got a better carbon profile. You know, they create this really welcoming and kind of warm space. You see in this picture here, you know, like that's a space that does not look like any of the offices that I get to work in. A few of our RDH offices actually get closer to looking that. But yeah, it's kind of a trendy thing right now. I don't know whether that trend will carry, but I think it's got enough momentum that this is worth worrying about this topic of moisture in mass timber. So what is mass timber? So we take logs and we cut dimensional lumber out of them, so 2x4s, 2x6s, and so on. And then we start to take those pieces, those smaller pieces, and we assemble them together. So we're basically making engineered wood elements. This one that you see here is, might be nail laminated timber or dowel laminated timber, where each of my pieces of wood are lined up vertically, like joists, just all kind of squished together. This actual approach is not new. We used to build mill buildings like this, where we would put up beams and then we would put all these boards together, and you would have a very strong floor that could handle heavy loads. This next one here is cross-laminated timber, so you can see that alternating layers run perpendicular directions, okay? This is the one that we probably see the most often, although I've seen more than a handful of buildings with the nail laminated and the dowel laminated timber as well. This is what it looks like when you actually get a panel. These panels, typically 5 or 6 feet wide, 20 feet long, 30 feet long. So they look kind of like a precast concrete slab as they're being craned off the truck, but made out of wood instead of concrete. Here, a quick little summary slide that shows you a whole bunch of different variations of this. So glue lam, which is something that I think that you've all seen, goes way back, probably 80 or 100 years, but these other ones are kind of newer versions of that. So, is mass timber similar to post and beam? I already showed you a bunch of different photographs of some post and beam buildings that are all newer buildings. I'm going to show you some images of older ones. The one on the left there is from around 1926. Actually, that's John Straub's family farm that he grew up on. He said that it's inscribed on the door in 1926. So a post and a beam building, been around for a little while. Gets wet a lot, dries out a lot. The one on the right, 1250. So 800 years we're coming up on? You know, is this stuff durable? Does it last? Oh yeah. Now, is our mass timber like post and beam? Not quite. Well, these are pretty good sized pieces of wood, like maybe 8 by 8 or 10 by 10 inches. They're not 14 inches thick and 6 feet wide. Okay, so smaller pieces of wood behave differently. Is it similar to precast or tilt-up concrete? I said, you know, you crane it off a truck kind of like you would a core slab. And is core slab a name that folks are familiar with if you're not from Canada? It's precast concrete with the cores through the middle of it. Well, yeah, you crane it off the truck, and often the same crews that are putting up mass timber are the same crews that put up the precast, but it doesn't behave the same. This is a building that's not too far from my house. I've been watching it go up all summer and horrified as they put the drywall on the inside and there's no windows there and the rain's going in. You could see in the corner there. And I was thinking, man, how would I feel if I was the construction manager and they told me that my windows are going to be 3 months late? Do I delay everything or do I just gamble and go? You know, concrete could take a lot of wetting. It doesn't care about the water. So the difference is here, well, I've got a lot of mass timber buildings being assembled by people that, you know, in their earlier careers were assembling post and beam wood buildings or assembling concrete buildings. The mass timber doesn't behave the same way. It doesn't dry as easily as the post and beam because it's too big, and it's not as tolerant of the water as concrete. And so there are some differences here. So we've been working on these for over 10 years. I think the first one that we did was UBC, first major one we did with UBC almost 10 years ago. As I said, we've done over 50 projects now. So we've got buildings that have gotten really wet. We've gotten buildings that we've actually been able to keep dry, and they've done incredibly. And then we've got buildings that have had 5 or 10 years of service. So they're not just newly built things. And so we've learned a lot. And as I said, we've got many projects that have been successful, not just ones that have gotten wet. So I don't want to scare you away in thinking that we can't build these. You can. We've tried to share that experience with the industry. And so we've written a few guides. We've participated in other guides that other organizations have made. But really it's about starting dry and staying dry. And so our first guide there, and I've got the links for you, moisture risk management strategies for mass timber buildings. That's about how to build it. So keep it dry during construction. Stay dry is about designing it in a way that it's going to remain dry during service. So good links to follow up on. Again, I said I was going to give you like 8 slides crash course on mass buildings, and now we're going to get into what I really wanted to talk about today. And back to my brother. So that's me on the left and my brother on the right. I think we're like 9 and 8 years old. That was the week before I met Joe. And I said my brother and I, we're close together, and we've had the same group of friends, and get along really well at this point in our lives, but we're not the same people. I'm the type of person that I can read something, or you can tell me something, and I will learn a lot from it. My brother doesn't learn that way. My brother learns either by seeing something, you show him, or he has to experience it firsthand. So right around this age, you can see in that photograph on the left there, I've got my captain's hat on. That's because I didn't want to wear the straw cowboy hat that the photographer told me I had to wear. But I'm holding on to my dirt bike handle. At this point in our lives, I would build ramps that were 4 or 5 feet high, and then my brother would go sailing off them and ask me to make them higher. And every once in a while I get hurt, and my mom would say, "Chris, you can't treat your brother like he's a crash test dummy." I said, "Shh, he thinks he's a test pilot." So, I'm thinking about, how do we communicate with people that learn by either seeing or living it, not just reading it? I'm going to do a little demonstration test so that we can see it. So, wood, mass timber, and water. So how does mass timber get wet during construction? On the top image here, I've got a laminated timber element. You can see there's some cracks between some of these top pieces of wood there. Water gets down into there. Water runs over the edge and soaks into the end grain of the wood. If I take some of these panels and put them together, I've got a channel here and a spline goes on that. Water gets in under the spline and again flows down over the edge. That's my connections also allow me to get water in them. And then as I get into assemblies, I add maybe an acoustic mat and a topping slab on here. And that adds another source of water. It's not just the rain, it's also water that's being built in. But I've got water that's moved by gravity. It drains downhill. That's the fastest thing, and it looks for the biggest cracks and the biggest gaps. I've got water that moves by capillarity through smaller cracks and gaps. That's also relatively fast. And then I've got water that moves by capillarity right into the fibers of the wood. So that's pretty slow. The smaller the fibers, the slower it's going to be. And then I've got adsorption, which is just the water that adsorbs from the atmosphere, water vapor, into the wood. That's extremely slow, okay? And that's got to be driven by vapor diffusion. So let's think about a few of these. In this image here, I've got a little bit of a video here. You can see water draining down. That water's pouring between the gaps between the CLT panels. So there's a lot of water coming off. And this would be not unusual on some of the job sites that we go to. Are the construction managers and the general contractors reckless? No. It's a new technology. They're relying on the trades that are there to put it together to give them some guidance on what they need to do to protect it. By the time they realize that the guidance they got was incorrect, this has already happened. Okay? So we're learning, it's just we're learning slowly. I'm trying to get us there faster. Now, why is this happening? Or, the nature of the construction is that we put these things up and we can't water protect them fast enough. We're going to come back to that. What happens when that water crosses the wood? Well, wood is a really interesting material because it's not the same as you go from one part of the wood to the other. It's not the same as you go in one direction or the other. So we know that water wicks faster along the grain than it does against the grain. So I've got these 3 different orientations I'm going to look at. And if we actually wanted to look at it under a microscope, we'd see that along the grain, I've got these long pathways that you can see they're going to pull the water along long distances. Whereas if I go against the grain, it has to keep crossing through these cell walls. And so it really slows it down. That nature of the structure of wood is controlling how fast the water moves, liquid water moves, and how fast water vapor moves, okay? And so we look at it, in a little bit, a drawing here. This drawing's from the 1940s. These are pretty, before they actually had these powerful electron microscopes and so on, somebody actually looked under optical microscopes and drew these things. It's pretty awesome. So this, if you look at that, okay, you can see the different, like the cross grain versus the along the grain here. And along the grain, it kind of looks like a bundle of tubes. So I want to reference back to John Straub's presentation last year, he gave one on capillarity. So 2022, that was, I guess, 2 years PC. Not politically correct, but post-COVID. You can follow that, but the gist of it is this. Hygroscopic porous materials are going to wick water, and the pores that are bigger will not pull with as much suction, but there's less flow resistance, so they fill very fast. The pores that are smaller pull with really high suction, but there's flow resistance, so they pull slowly, okay? Wood is made up with a mix of those, right? And it turns out that it's going to move liquid water much faster along the grains than it does against the grains. There are tiny little holes that connect from one of those kind of bundled tubes to the other that'll pull against grains. Now, wood and water vapor diffusion, again, it's moving along those open paths inside of wood. And it turns out that as the wood picks up water and gives off water, those paths open or they close. And so this is actually a really cool graph from 1950s from Joy. And you'll see here that on this bottom axis, this is looking at the humidity, the relative humidity on one side of the wood. And then these curves up here looking at the relative humidity on the other side. So let's say that I've got wood that's really wet, 90 to 100% RH on one side, and it's really wet on the other side, it's 80%. And I've got wood that is like somewhere around 5.5 perm inches, okay? Now what happens if it gets, it's still wet on one side, but it starts to dry out on the other side, get down into 20, 30, 40. Now it's down to like 2 perm inches. So as the wood starts to dry out, it starts to get more and more difficult for water vapor to diffuse through it. Okay, so it starts out diffusing really well, and then as it dries, it becomes much slower. Now let's look at some of these mechanisms here. This is a time-lapse video of water being pulled up through plywood. You'll see on the left here, that's wetted right to the top, just as I've been introducing this video. On the right here, you can see that it's slowly wetting up across those glue layers between the plies. And then this one in the middle here, you're seeing it wet up the face, and you can see how it kind of wetted up to this line and then went around, and now it's wetting up above it. It moves in really weird ways. It's like fire. You're not going to predict it. You just have to know that you can't predict it, and there are kind of like general things that you're going to pay attention to track it, right? So what I know that all these wood fibers are going to pull water, and I know that the cracks are going to pull it faster, and I know that these kind of big gaps and voids are going to allow it just to drain. But this is a chunk of cross-laminated timber, relatively new, never put into weathering, and you can see all those pieces are there. We've got the gaps of the cracks, bigger voids, smaller voids, joints, and so on. Now, as that thing weathers, so it gets wet, it dries out. Every time it gets wet, it expands a little bit. Every time it dries out, it shrinks a little bit. And it continues to see that weathering. And what happens is those gaps and cracks get bigger and bigger. So as those materials see weather, I get more holes and more pathways to get water into them. I like to think of water wetting these mass timber systems kind of like traffic in a big city. So if you imagine we all got in our cars tomorrow morning, we drove right into the middle of Boston, and we're going in on the interstate or the freeway, and it's like 5-6 lanes wide. How many thousands of people are going into the city really quickly? And then while we're at whatever event or whatever work we're doing for the day in Boston, the highway gets closed. And not only that, all the cars stop working. And so we've got to walk out on trails or ride bikes. What's happening here is these big cracks take the water straight into the city, and then it goes into the wood, that now you're in the building, but it doesn't go back out the big crack. Now it's got to go out through all the little pores and all the tiny cracks. So it's easy to put water in, but it's hard to get water back out. Now, hopefully, when we're building buildings with this mass timber elements, we don't leave them exposed as long as this one has been, so we don't see this level of cracking and so on, but it gives you a sense. Now, all this little backgrounder on wood, I could explain this to my brother and he'd be kind of, so we got to get to some demonstrations. So I'm setting up some little tests here to look at wetting and drying of wood. So I've got some of my cross-laminated timber, my CLT wood samples, and I'm going to cut 4-inch by 4-inch blocks out of it, and I cut them very specifically so I've got some edge-to-edge joints here. On some of these panels, those edge-to-edge, like four-side square, whatever. Square four sides. Now I got it. They're all square four sides. Some of them are just glued on the faces, and the two sides are just touching each other. Others are glued also on the edges. The ones I've got here are glued on the edges. And so I've got one edge in the middle layer, another edge in the top and the bottom layer. So I've tried to include those joints. Now, I was talking with, where's Ali? Anyways, he was asking me, so what does that glue do to moving a water? Like, does that stop it? Like, it acts like a barrier? Let's see. So I'm gonna wet these. I'm gonna put them into what we call an uptake test, and we're gonna allow water to wick up into them over the course of 24 hours, and we're gonna continue to take photographs, and we're gonna continue to weigh them over the 24 hours. And we put some dye in there to see what's going on. And you'll see that on the left-hand side here, I've got one that it's wicking straight through the face, so it's going through the side grain. I've got one over on the right here, where I've got the middle ply, so that it's got the end grain in contact with the water, but the two other plies have side grain, and I call that edge. And then I've got double edge, which is this middle one, which has got the two sides have the end grain in contact with the water, and the middle not. And you can see here a few interesting things. Where's Joe? So Joe, you know, we have that conversation about, does the dye impact the way that the water wicks? And you know, Joe and John and I have had a chance to play with a few different dyes, and a few of them we've looked at, and no, it doesn't seem to. This one incredibly seems like the water and the dye do not follow the same timing or path. You can see more clearly here. Here's my water line right there, and the dye is kind of following it, but there's some other interesting things here. See right here how it's following the radial path? And the dye kind of is wetting like these little, like almost like tiger stripes. It's because the dye is being pulled through the early wood, like when the tree grows, it grows faster in the spring and slower in the fall. So they've got early wood, bigger pores, late wood, smaller pores, and it doesn't track through the smaller pores as fast. You can actually see it in this. Again, here you can see the water tracking way ahead of the dye. On this one, I can actually see, probably hard to see here, but you can see that the water's coming up higher through this one. Well, that's through the end grain rather than through the radial grain and so on. Other interesting thing, and this goes back to the conversation that we were having about what does the glue do? You know, if I actually took edge glued, do I get rid of a crack that would track water? Many people assume that's what's going to happen. I don't like assumptions because they keep kicking my ass. So I test them. What do you see here? All these little wet spots. Each one of these corresponds to the joint between the wood. So despite the fact that those edges are glued, they're still wicking water faster through those joints than it is through the fibers of the wood. Now, when the thing dries out, because it didn't pull the dye up through that, I can't see it anymore. If I didn't have this photograph during the test as evidence of it, I'd say it didn't happen. But a little lesson there. So I said we were taking photographs of this, but the other thing we're doing is measuring. We're measuring the mass of it. Why? There's lots of different ways to measure the moisture content of wood. There's only one way that you can't argue with, gravimetric. On the left-hand side, I measure it dry. On the right-hand side, I measure it wet. The difference is how much water's in there. I can't tell you where it is, but I can tell you how much water's in there. So we did this wicking test. What did we find? Well, I found that the sample that I had so that the face was touching the water, had no end grain, is pulling in about 1 ounce of water on the right here. It's about 30 grams. Whereas the one that had the one ply with the end into the water pulled, well, not quite 2 ounces, but close to double. And then the one with two plies with the edge in the water pulled only a little bit more. That's interesting. You know, that's kind of counterintuitive to me. I would have thought that the two that had the end grain, like the double end grain in the water, would have pulled it significantly more. Why do you think that is? I don't know for sure, but I think it's because the joint between the pieces of wood dominates. It dominates over what's pulled up into the fibers of the wood. Okay, so let's keep going. You know, I got a fair bit of water in there in 24 hours, but I also know from what I've measured in the field that that's nowhere near enough water to reflect what we see on building sites. So let's pretend that we're the mafia, and these blocks of wood are going to sleep with the fishes. So you may know that wood floats. And so if you really want it to stay in the water, you got to put a weight on top and get down. 25 pounds on there. So we put these blocks of wood in the water for 24 hours. It's going to absorb a lot more water, right? So many of my hypotheses are wrong. So how did I have the samples that were wicking water absorb more water than the sample that was fully immersed for 24 hours? Pressure? There's nowhere for the air to go when it's wicking in all 6 sides. So the samples that have just one side, one face in the water, water comes up, it pushes the air out the other 5 sides that are open. Put the whole thing in the water, water wicks in through 6 surfaces, but the air can't get out. It's got to diffuse out slowly. That's cool. Okay, so I'm still disappointed because the amount of water that's in there is nowhere near what I know happens in real life. I soaked those for 24 hours. What happens if it's not wet for like hours, or what if it's wet for days or weeks? This was one of the first mass timber buildings that we built in, that our team worked on in Toronto. I think it was the first mass timber building in Toronto. And it unfortunately was built a winter that we didn't have very cold temperatures. We didn't get a lot of snow. And the spring rains came early. And so the construction team was kind of caught unprepared. We had a moisture protection plan which said they were going to tarp all the sides of the building. And if we got incidental amounts of moisture onto the floor, they were going to squeegee it off. The first afternoon they squeegeed it off. It kept raining. The next morning they squeegeed it off. That afternoon they squeegeed it off. And then they said, guys, we're going to squeegee it off when it stops raining. That was 14 days later. So we came in and we said, this is really wet. How wet is it? Well, we measured it, and it was over 30% at the surface. Now, many of you will have different versions of pin type moisture meters, and they typically have pins that are how deep? Like 3/8 of an inch? And so I stick my 3/8 inch long pins into the top of the plywood, and I'm like, oh yeah, 30%, but also, should know better than to trust what's in the top of the plywood, so I get longer pins, and I push them in 3.5 inches from the bottom, 7 inches from the bottom, which takes me to like 1/2 inch from the top. And I push another one from the bottom right into the plywood there. I put them from the bottom because I knew we were going to put a concrete topping on this, and we measured these. And our hearts stopped because, oh my God, it's like 40% moisture content in the middle of this wood. Now, this is an NLT panel, so all of the pieces of wood are stacked up like vertically, so water got deep down into it really easily. Well, Chris, what do we do? 40% moisture content, is that bad? I'm like, well, it's kind of a concern. Did you measure the rest of it? Well, okay, I'll map out like a few spots. Let's pick 5 spots, we'll measure them, and it's like, oh no, some of it's higher than 40. What is it? I don't know, because the meter just tops out. It says, hi. And I don't think it's saying hello. Help would require more digits. So, okay, suffice it to say that my little lab test here, where I've like soaked some pieces, letting it wick the water up, and I sunk some of it down and it's not soaking in, is not working. I need a new device. This is what John Straub calls a vacuum chamber. That's boring. I call it a wood wetting time machine. So you can see the wood in there, the dome over top. This is the thing in bigger arrangement here. That's the bubble thing that you saw the samples in. It's connected to a vacuum pump. Any of you guys who work in HVAC, you recognize vacuum pump? Yeah. And I could buy a laboratory vacuum pump. It's like $10,000. Or I could buy an HVAC vacuum pump for $1,000. John and I are cheap. HVAC vacuum pump, but we pull all the air out of this chamber for 8 hours. And then while it's under vacuum, we flood it. Remember, so the air had no way to escape and let the water in. If I take the damn air out, then it's not gonna get in the way, is it? Big brain. So we wet the wood. And so the way, by doing this, we're able to get amounts of water in here that would probably take weeks, many weeks to actually wet it. And this is what we find. Okay, now I got some water in there. And it's right in there. Remember how I said the wood floats? It doesn't when you put that much water in it. For the record, that's around 140 or 150% moisture content by weight. Okay, to be fair, that's more than I was measuring in the field. But to be fair, I don't know how much I was measuring in the field because the meter said high. This is gonna do us well for our demonstration purposes. Okay, so I need one more thing here. I need a different material. I need a different material so I can compare what I think is going on with the wood to what we, the greater industry, thinks goes on with other materials. So I picked wood or mineral fiber insulation, stone wool. All right, and I took 2 pieces of 2-inch thick stone wool, cut them 4 inches, stacked them together, so now I've got a 4x4 stone wool. Why didn't I take 4-inch thick stone wool? Because I didn't have any and I was running out of time to get this done before I came to this conference. Anyways, so I wet that. Now, first thing you're gonna say is you're gonna say, oh my God, Chris, 7 ounces, it absorbs so much water in 24 hours versus the CLT, yeah? Wait till you watch it dry. So, now we're to the drying part of the test. Got wet wood samples, some of them wet just kind of on one surface, some of them wet on all 6 surfaces, but really shallow. It's all on like the outer faces of it, and some of them wet right to the heart, and they sink. And then I've got my stone wool. And so I set up a little test like this. I've got 3 pieces of wood and 3 pieces of stone wool. I wrapped the perimeter of them with like 10 wraps of cellophane, or the wrap that you use, saran wrap would be the brand name, right? Like you're wrapping a sandwich. Is that a vapor barrier? Is that as good like a 6 mil vapor barrier? No, but it's a lot easier and faster than, and it's gonna be sufficient for what we're doing here today. So I take 3 pieces of wood, 3 pieces of the mineral fiber insulation. These are all the ones that were like wetted really heavily. And I put them into a little group and I'm gonna call that no assist. What does no assist mean? It's drying just to the environment. I'm doing nothing else to encourage it. The next one over here on the left, I have a fan that keeps blowing across it, right? You know, we had a little flood, let's get the air movers out, let's dry things down. On the right-hand side, I've got another set at the front here where it's heat. How many folks here are from the restoration industry? Okay, yeah, a few of you. There's the arguments about, oh, do we need heat, do we need fan? Ha ha ha, pay attention, this gets good. Oh wait, if fan and heat are good, what if we put fan and heat together? We'll do this guy here. All right, and just so that you know that I'm not silly enough to let the heat from this light get back to the no assist, I put barriers. Also, so there's a barrier vertically here, and then there's other barriers there. That's so that they can't see what their neighbors are doing. No cheating, yeah. Okay, so now we get to the good part. You guys wanna see what's happening? All right, this is the way we're gonna measure this. On the right-hand side here, this is drying rate in ounces per square foot per day. On the left-hand side, grams per meter squared per day. And the no assist, we're losing, just like this is like in the first 6 hours, we're losing at a rate, and again, I'm measuring this gravimetrically, so there's no doubts here about how much moisture's gone. I'm losing at a rate of about 1 ounce per square foot per day. Okay, not bad. So what do you think will happen if I add the fan? It's gonna be better, right? Right on, almost double. 50, 60% better. What about the heat? More or less than the fan? I hear a few less, a few more. Well, if you said more, you were right. Right, although they're pretty close. Okay, so now we're in like the 2 ounces per square foot per day land, okay. Fan and heat together, oh yeah. You know, not quite, but yeah, almost 3 times what I have with nothing. Okay, you know, those drying folks are onto something, right? But this is in the first 6 hours. What happens if we keep going? Well, if I look at it in the first day, it's like, oh, okay, you know, there's my no assist, and I'm still, you know, as it starts to dry, initially it's all the drying from the outside surface, right? And then as it starts to dry, that water's deeper inside and it has to diffuse to the surface before it goes out, or it has to wick to the surface before it goes out. How much water wicks through stone wool? Nah, not much. So it has to basically diffuse. Now, luckily, stone wool is like really vapor permeable, so it diffuses pretty fast. And you see that it continues to dry itself out kind of nicely. What happens if we look at the fan one? Oh, initially there was this kind of slower rate of drying, and then it started to actually speed up, and now it starts to drop off again. Heat, same thing. In fact, at this point here, like, 30 hours into it, well, now the heat is actually not even going as well as the fan. Well, the reason it's slower is because it's actually dried out more of it, and what's the heat doing? It's driving it down to the bottom. Now, what I remember to point out to you is when I set this up, I set them all on grids so that they could dry from the top and they could dry from the bottom, because that's what a CLT slab would do, floor, right? Dries up and down. What about the fan and heat one? Woo! And if we keep going, I see that, okay, my no assist one actually keeps drying down and down and down. Around day 7, my drying rate looks like it's getting to 0. It's like, oh man, I'm not getting any more drying. Yeah, Chris, because there's no more water in it. Okay. Did I dry any faster with the fan? Yeah, you know what? Around day 4 or 5, already dry. How about with the heat? Also around day 4 or 5. So the argument about heat win, fan win, in this particular case, same answer. What about with the heat and the fan together? Yeah, pretty solidly like a day ahead of everything else. This is a very vapor permeable material, okay? It's like you throw your clothes in the dryer, you heat them up, all the water leaves, and then you've got dry clothes. This is similar. Many of the folks that I talk to, when they're thinking about drying out a building, they think that this is how it works. Well, there was a flood in my mom's basement, and the restoration folks came in and they had it dried out in 3 days. You just showed me it dries out in 3 days. 3 days is the answer for drying any building, right? No. All right, so let's look at it a little bit differently. This has been drying rate. If I actually look at how much of the water that was in there to start dried out, and so here you can see tracking the no assist one up, and I've dried out 100% of the water actually around day 5 to 6. The fan and the heat one and the fan and the heat one are all in around day 3, 4. Okay, so what have I learned? Looking at this mineral fiber insulation, well, mineral fiber has no meaningful capillarity. It doesn't wick. I knew that because when I put the pieces of the mineral fiber into the water to make them like suck the water up, they didn't, and I had to hold them down with the weight like I was drowning the wood, sleep with the fish. All right, it's wickedly vapor permeable. I know that from studying its vapor properties, but it's demonstrated here too. And those two things together mean that this stuff dries pretty quick. The assists, airflow, heating, and so on, actually make a meaningful difference. And as I said, many of the people that I talk to think that this is kind of the way most of the stuff that we're dealing with dries out. Now, here's where it gets a little bit more complicated. What happens if I'm talking about my wood? And I say, okay, I'm gonna take those wood samples that I immersed for 24 hours, and they absorbed a bit of water, not as much as I wanted, but it was all kind of in the top, maybe 1/4 to 3/8 of an inch around all the 6 surfaces. Here's the drying of that wood, this gray line. And you know what? It's at day 7, 8, it's 90% gone. Actually, it's kind of drying like the mineral fiber did, or like my clothes do when I hang them on the line. This is propagating my belief that things dry fast. This is what my brother, but it dries fast, Chris. Like, that's been my experience, Chris. It dries fast. It's like, okay, but I get that. What happens if the moisture is not at the outside? What happens if the moisture is in the heart of it? That one. And so after the same amount of time, now I've only dried like 30% of it. This is why I think I'm running into trouble communicating with folks. A handful of people have this experience. Oh, don't let it get too wet, because if the water gets in deep inside of it, it dries slowly. Other people are like, well, my experience was that we dried the building out really fast. So there's these conflicting experiences. Both of them are true. But you're gambling if you think that, well, my building gets wet, it's going to be in this situation, not this situation. You don't know. it's better just to protect it so it doesn't get wet. So all right, let's look. This is how much was dried over the course of the week. What were the drying rates? Interestingly enough, the lower gray line with the squares here, that's our shallow moisture. The drying rate's been slow the entire time, but it also was all at the surface, so it didn't matter. The deep moisture one started with a really high drying rate. And again, these are all with no assist, so actually faster than the stone wall. But it had so much to remove, it just couldn't keep up. And you can see down here, now it's like into this almost flat line. And you know, it looks like it's not going to give up the water. We actually use this to our advantage in some of the applications that we employ wood in. Joe would appreciate this. Joe, do you know where this is? Man, you've done some renovations. I gotta go visit. I think this is Opus 1, but I mean, we actually, like, we design wine barrels so that the water, or the wine, and the vapor, the moisture, has to diffuse against the grain, slow, right? And it keeps the wine in there long enough, they don't lose that much, they can actually age it properly. So, you know, we know that these, this behavior of wood exists, and we can use it to our advantage here. We want to make sure that it's not to our disadvantage in our mass timber construction. So, we've seen that the stone wool dries really fast and that those assists make a difference. We saw that the shallow wood dried really fast, so we didn't really care about the assist. What happens with the wood pieces that have deep water in them? Do the assists make a difference? Yes? Yes? Yeah. I'm looking at my front row here, people that I really rely on to be keen, and there's only one person saying no. Mark, like, why do you doubt? Because you're right. It made no difference. Sure, in the first, if we were betting on the first day, then yeah, we'd all be laughing. Mark, see, you don't know what's going on. And then by day two, Mark's laughing at us and say, I did know what was going on. Why? Because the water that's deep inside that block of wood has two ways to get to the surface. By wicking, capillarity, which is really slow, or by vapor diffusion, which through the wood is really slow, and it dries, just gets slower. And so as we're traveling along here, it doesn't really matter. And so I'm in many situations where there's a debate about how are we going to dry this building out? And people will argue, we're gonna add heat to it. We're gonna run fans across it. We're gonna get desiccant dehumidifiers and put like minus 40-degree dew point air across it, and it's all gonna make it dry faster. No, all that does is impact what happens at the surface, and our problem is getting the water to the surface. Now, the interesting thing here is, as I get through the first 7 days and I'm looking at the wood looks dry to the touch. This is how the building tricks us. Because in real life, on real job sites, this is what people do. They take their meter and they stick it into the wood and they say, Chris, I measured it. It was 16% moisture content. We can put the insulation on now, right? What was the mass of the water in there? Well, you know, if I had 20 ounces in there, I still have 12 ounces. You know, it's still at 60, 80% moisture content by weight. It's just, it's in the part that you're not measuring. So, what do we learn by this? Well, mass timber's properties vary quite a bit. Capillarity, faster along the grain, slower against the grain. So it can be significant, but it depends on where it is and what the grain structure looks like. Has relatively low vapor permeance, and as you dry it, it gets lower and lower. That means that the water near the surface dries fast, so my shallow samples dried really fast, supporting my brother's thinking that wood stuff dries fast. You know, our jobs in our late teens were as framers. We had projects all the time that got rained, and the next day it looked like it was dried out. A 2x4 can get wet and dry out in a day. When you've got 8, 10 inches of it deep and many feet wide, it can't dry out if it gets right in the core. So that deeper encapsulated wood is slow to dry. And the assists don't help us with the deep water. This is a surprising thing for many folks. So I've kind of done this demonstration, but in tiny blocks of wood. What does it actually mean for our real projects? We've done a number of these. We've done a number of these where things have gotten wet, and we tried to figure out how to dry them out, evaluate different drying strategies. And we've done a few also where we're looking at, we knew that we were adding water to the system. So in this particular assembly here, I've got my CLT, I've got a membrane on top of it, and then a topping slab, and then I've got some type of sealing finish underneath. Now, really, the best projects that I, from my point of view from an appearance, are the ones where I can actually see the CLT, but there are these little things called fire codes that sometimes require that you cover it back up. So I'm gonna look at this actual building where we looked at the roof assembly and we said, we've got this 5-layer CLT here. We're adding a concrete slab to it. There's going to be an air vapor barrier there, and then many inches of insulation, and then a roof membrane. If this gets wet, right here, it can dry down, but how much can it dry up? Not at all, right? So we don't want that to get wet. It gets more annoying because it's actually put on top of this, where I've got a glue lam beam turned on its side, and then it's a structural composite slab. So there are a bunch of shear studs in here that are connecting this concrete beam into this glue lam. And I've got my CLT slabs here and the edges exposed and so on. By the time I put my roof assembly on top, I get that. And this is what I want to look at in my model. So I say, okay, I'm gonna model this part that I've identified in this red box, okay? So I'm doing a 2-dimensional model of the assembly. Now, before we put the concrete and the insulation and stuff on there, I basically have a glue lam beam, and you'll notice here that I'm cutting it down the center. That's why it looks funny. Why? Because the model's annoyingly slow to run when you do something that's complicated, and this speeds it up if I only do one side. So in your imagination, you have to say that this is the right half and the left half looks the same. I know the right half and the left half never look the same, especially in the US. Doesn't look the same in Canada either. For the purpose of this, it's the same. So glue lam beam down here, CLT slab up here, all right. First thing I'm gonna do is I'm gonna say, okay, if we put this up and then it sees rain, let's hypothetically say this is in San Francisco. I'm gonna pick April and I'm gonna say what happens in days of rain. And so you can see down in the little corner here, it says day 4. And it's predicting moisture changes. Now, on the right-hand side here, I've got a little scale. All these green colors are relative humidities up to 80%. The yellow one is between 80 and 85, orange 85 and 90, and the reds get into the 90 plus. Why am I using relative humidity? Because as I move from one material to another, the relative humidities are staying the same, the moisture contents aren't, so it's easier to use the relative humidity. But suffice it to say, it's wood. Once we start to get above 80%, we're concerned. Once we start to get above 90%, we're like, rather concerned. And when we're getting to like 98 or 100%, now we're really concerned. Yes. All right, so what do you notice here? The way that this model's set up, the rain is hitting this. It's like ponding on the top a little bit and soaking in the surface of the wood, but slow, just like our model, just like our actual tested, right? It runs over the edge. It soaks in the end grain of the wood here, and where else is it soaking in? The horizontal glue joints. And it soaks through the vertical glue joints, right? And as I keep going, so there's a week of it, they got a few good rainy days, it picked up a little bit more. It's halfway through the month, getting towards the end of the month. Chris, does 4 weeks of wetting really mean you've got water that deep into the wood? Yeah. Where's it going in? Well, it goes in all those glue joints. But water can't move through those glue joints, just demonstrated that it did in the photographs. Model's showing the same thing. So what did we learn from this? We learned that when we put this up, we're gonna tarp it so that it doesn't get wet by rain. All good, right? Okay, step 2, we're gonna pour concrete on top of this. Isn't the concrete gonna add water, Chris? It's like, yeah, so we just protected it from the rain for 4 weeks and now we're gonna pour water on top of it? It's like, yep. Okay, so there's the initial bleed water from the concrete. And it's gonna dry out, right, Chris? There's month 3, 4, 5, 6. It dries out in a few months, Chris? It's like, well, there's a year. okay, let's do a different thing. Let's use water with like a good additive, so we can use a low water to cement ratio, get the plasticizer so we can actually pour it and get it all settled out and everything. Less water. Yeah. No, less water was not the answer. Okay, all right, new idea. Let's put a membrane there that will stop the water from soaking in, right? But we'll make sure the membrane is vapor permeable so that the concrete can still dry down, right? So no wicking, but water vapor diffusion, okay. So there's not bleed water in, but vapor diffusion and adsorption, folks. No liquid water. Still drives it. Okay, so maybe the membrane was a good idea, but it needs to be a vapor impermeable membrane. Let's go down to 0.5 perms. Oh, that's looking better. Actually, that's not bad. Okay, well, 0.5 perms was good. Let's go to 0.015. Ooh, oh, look at the wood's drying. Yeah, the wood's drying. The insulation above it is completely effed, but the wood's drying. What are we gonna do here? You know what? Somebody said, what if we were to put a vapor permeable coating on the surfaces that don't wick that much water and put a vapor impermeable coating on the surfaces that do wick a lot of water? Huh, that's actually kind of interesting. Now, I've had a number of these projects where I really tried to convince the panel manufacturers to put a membrane on the panel in the plant, and they really don't want to do that because it significantly slows down their fabrication. We got one of them to put it on. Do you know what happened? The panels came to site, they were covered with this nice membrane, they put the splines on, and then the engineer had to come and inspect the splines. So those parts didn't have any membrane on them, and then it rained, and then the membrane stopped the water from soaking in the top, and so it pushed it all off the side and down the side where it's most susceptible. And then I thought, yeah, the membrane was more expensive and more annoying for everybody, and it didn't really help us. So now my favorite thing is spray it with a coating that's going to make some difference, and then we will try to protect it as quickly as we can once we get up. Now, what's as quickly as we can? You know, if we protect it with a coating and it gets a day of rain, we're gonna have shallow water in it. 2 days of rain, shallow water in it. But if we can actually get it to the point that it only sees 2 days of rain and then we cover it with a membrane, we're good. What happens in those 2 days? Hopefully it doesn't rain, and hopefully the structural engineer comes and improves the spline. So, concluding thoughts. There's a fair bit of industry guidance available on this, and you can see just by me doing this that we are still learning the answers. We've got lots of successful mass timber buildings. They did take a little bit of care, but if we know what we're doing, we can make that happen. And the GCs, the construction managers that I've worked with that have had these problems, have completely changed the way that the job runs. They get a new crew in. This crew has lots of experience assembling precast concrete, and they say, we know what you guys are thinking. We've been bitten by this dog. We're doing it this way. So we've got the solutions. We've learned that it's not like light wood framing, it's not like post and beam, it's not like concrete. We know that there's a disproportionate number of buildings that are having that problem, and it's the deep and the encapsulated moisture that we need to avoid. What I'm asking you guys to do is share this story, because we're gonna build more of these mass timber buildings. I want them to work. I want them not to call me and say, how do we dry this out? Thank you for your time.
Chris, my takeaway is that you're going to wake up one morning with a dehumidifier in your bed.
So my question has to do with in the drying and the shrinking and the drying and the shrinking, does the dimension of the CLT start to distort and degrade and its structural ability be compromised? Because it's going to be different at the middle than at the ends.
It can degrade. The CLT is more dimensionally stable than some of the other formats. The NLT and the dowel laminated timber, where you've got them all stacked up side to side, we'll actually see them expand and start to buckle like the sidewalk does when it gets hot.
Okay,
But it
want
does change.
I want to interrupt, make a quick announcement. There's going to be a meeting on unvented roofs in the living room at 5:30 for those that were interested in that. And that's the only important announcement. Please continue to ask questions.
How many questions do we take?
Well, as many as you want. And we'll see you in our backyard.
Right. And those of you who are off to go and enjoy good food and drink, have some for me. I'll be there shortly.
So Chris, what's happening to these ones that you see that are getting deeply wet months and however long you've been able to look at them? Are they like rotting in the middle?
I was hoping nobody would ask me that. Are they rotting? So the first one we built that really got deeply wet, the models convinced me that it didn't matter what we did to dry it, it was not going to dry faster than a few years. The developer agreed to allow us to monitor the drying, hoping that our predictions were wrong and what the timber building guys were saying was right. And at year 3, we were tracking within 5% of the prediction, which to me is exactly the same answer. And at year 3, he said, please stop telling me what's going on. But there was a debate. So they said, well, is there going to be a decay problem? And I'm like, it's in the moisture range that we would be worried about decay. Is there going to be a mold problem? I'm like, well, it's well above the moisture range that we would worry about mold. I said, but everything that I know about mold is on surfaces, and this is embedded deep inside it. I don't know what the rules are. Nobody does. And so we went around the table, talked to the structural engineer. It's what moisture content's okay? It's 40. Structural engineer says below 20. Is it okay above 20? Well, we don't know. All of our rules say below 20. And so we went all the way around the table, and every single expert said, I don't know what to say, and I'm not going to sign off. Finally, the developer said, I'll take responsibility. We're just going with it. Close the building. So as far as I know, they haven't had a problem, but honestly, I don't go back and look on purpose. We have one building in Vancouver where we're measuring 50% moisture content for a long time, and we were concerned about that. And so we took the topping slab off, and we lifted up the spline plates in their areas that are rotted. So what's the spline plate's job? It's to stop the panels, it's to transfer shear across the panel so it acts like a diaphragm, right? So you have to transfer it from this panel into the spline plate into the next panel with fasteners. And all those fasteners are going into rotted wood in an area that has heavy seismic loads. So we basically took that whole thing apart, dried it all out for a year, and now we're putting it all back together. So, I mean, any construction management or development folks here, if your entire construction schedule got delayed for a year, you wouldn't be sleeping. Those guys aren't sleeping. And now they're wishing that they hadn't had to get wet in the first place. So. Well, on the one in Toronto, the developer basically said, "Okay, I'm gonna own it." The one in Vancouver, I'm not sure, but it's a matter in process. I probably shouldn't talk too much about it.
So I have a question. Maybe I need to see your concrete and masonry lecture. But I think I was seeing in the WUFI model was that the concrete was wet, and didn't dry out over the year. So is there a concern about strength or any of those issues that we care about in the wood?
No.
In the concrete?
Okay, so there's no worry about the there's no worry about the concrete. The concrete actually likes being wet when it's curing. You keep it wet for, dams just get stronger and stronger, right? And concrete does take years to dry out. We pour slabs. We've measured basement wall assemblies. It's funny, even at the university, our concrete researchers decided they were going to embed RH sensors in the concrete. And at year 2, they said, they still say 100%, these aren't working. And John and I looked at him and was like, no, it's at 100%. And around like year 3 or 4, hey, they're showing 97. Yeah, now it's finally starting to dry. So the concrete I'm not worried about. The roof above it I'm worried about. And so the game plan there is like heavy vapor barrier above, heavy vapor barrier below, keep the concrete wet and let it slowly dry up and slowly dry down.
Okay, so is this now something, I don't know anything about, like the mechanical design, is dehumidifying a building over a long time period now an additional requirement of the mechanical design in CLT?
Interesting question. So I'd say we're still dehumidifying the building because we've got other sources of built-in moisture. What changes with a mass timber building is the way that we dry it. The knee-jerk reaction is, oh my God, it's all wet, we need to dry the heck out of it. Anybody who's dried wood, anybody who builds furniture knows that you don't want to dry it too fast. The whole game is to dry it slow so that it doesn't have a big gradient between the high moisture concentration source and where it's dry. So we'll provide guidance to them. Okay, we're gonna dry it, but we're gonna make sure that it dries at a pace that's not gonna cause it to crack and check and stuff like that. And we'll monitor it. And we might say, okay, we're not gonna let you make it 5% RH. We're gonna like slow it down into like 30. Watch how it's going. We might try 20. We might start to see it crack. Now let's go back up to 30. And so it's this kind of like cautious, like, act and watch the response.
So maybe the drying concrete as it goes through the wood might be helping that, moderate the.
It might. That's still, for me, that's that last situation I showed you there is the one thing that we don't have the best answers for. Everything else, I can tell you how we're going to keep water off of it. I mean, you see in this image here, the way the Europeans do it, they just build a tent over the top. But there are some things that are just going to have built-in moisture, and that roof one is particularly problematic because where I can limit the water on the floor and then allow it to dry up before I put more flooring on, how long can I wait before I actually put the roof insulation stuff on? Like the construction schedule is pushing me to it's been a month, Chris, can we do it now? But,
So, real quick, would you recommend to design some sort of pluggable vent to help with drying?
Pluggable vent.
Like a vent designed in the wall allows that vapor to escape in a direction that you prefer, and then after a certain time you can seal it up.
Interesting question, Anthony. So one thing that we have done is you saw there's, when I was talking about the floor, I said that there's often an acoustic mat between the CLT and the topping slab. One of the acoustic mats that we've seen used is actually a dimple sheet. It's like a 3/8 inch thick dimple sheet. And when we modeled pumping dry air through there, it does improve it. But again, the bottleneck becomes getting the water from the core of the wood up to that layer. So what did we learn? Well, on one hand, it's a 3/8 inch deep dimple sheet. You can't move a whole lot of air through it. On the other hand, moving a lot of air is not going to make that difference, but moving some air does. So yeah, we're playing with those types of bypasses. I wouldn't call them ports though, because if you make a port in one location, you've got to get all the water to that location. Whereas if you can spread that port over the entire surface.
Yeah. I mean, the design's gonna be based on size, location, stuff like that, right? Orientation also helps, but it was just a thought.
Yeah.
So there have been a couple instances where the adhesive between the layers of the CLT weren't selected well, and they sort of tried to address that. What happens to the moisture, to the adhesive layer, if it's got that kind of moisture in for that extended period of time? Does it re-emulsify? Does it?
So I have not worked on any of those where there was a poorly selected adhesive. Yeah.
What for that long, generally?
Yeah, but we're mostly talking about like urethanes and isocyanates and stuff like that, and they don't care that much. They're more tolerant. Yeah, if you've got something that's going to re-emulsify, then we're going to be looking at, are we taking the building down? Are we structurally supplementing it? But yeah, so at the back first. What about using a vapor smart membrane? Well, I think those are great products. I would not waste the money on it in that application. And the reason is because so the smart membrane becomes more vapor permeable with the RH high, and it's going to be high all the time. So why not just put a vapor permeable air barrier there? So it'll allow it to dry down, but yeah. Well, that was the one scenario that we looked at. We said, okay, well, let's put that vapor permeable membrane there. That'll stop the water from getting, but the diffusion still is too much. And so what we were doing with the other ones is we were trying to balance it. So we said, okay, when we use the 30 per membrane, it's still too much water vapor water by vapor diffusion. And so we went to the 0.5. It's like, oh, now that's looking pretty good. And then that made us think, oh, well, what does the 0.015 do? Honestly, the 0.5, 0.015 is probably a better match, but it is going to push water up. So. Yeah. So yeah, good question. And that's what we did with that one is, so the coating in the plant is pretty easy to apply. And some of the manufacturers, they just do it by default right now. Because they can spray it on, it's dry in like 15 minutes. What I say is like, put it on the top, put it on all four of the edges. Don't worry about the bottom. If you want to worry about the bottom too, great. That comes to the site. Now, is that as good as a membrane? No, but it's better than nothing. Now, comes to the site that way, if I get my wishes, then we also put a stronger coating around the edge when we know it's going to be exposed for a certain amount of time, or when we know that we're putting concrete on top and I don't want it to wick in. But you're right, yeah. Yeah, but the problem, we're willing to do certain things when we're doing like single houses that we don't want to do when we're building 6, 16, 26-story buildings, which is where this stuff is being used now. But last one.
I don't even know if I'm supposed to be using this anymore, but have you done any analysis or modeling on mass timber walls? And and do you recommend a permeable WRB or an impermeable? Maybe it depends. Maybe it doesn't matter a lot of the time.
I love this question. I love this question because my architecture class 2 years ago came to me. Actually, John was teaching the same group of students. They came to me and they had it was a master's class. They were having this debate and they had come to this kind of point where half the class was kind of on one camp where you should use vapor permeable layers on the outside and the other half was you should use vapor impermeable layers. And they came in and they said, which one of us is right? And I said, oh, this is an interesting question. Let's just use like the first half of our class to explore this. Is one right, one wrong? I'm like, well, let's see. So group that says you should have vapor permeable. Why? Well, if there's moisture in the mass timber wall, and we have a vapor permeable air water barrier, and then we have vapor permeable exterior insulation, it can dry out through that, and that's good. I said, yeah, that's a good point. That's a good argument. And so they said, so we're right. And I was like, well, maybe. Is there anything else that you have to worry about? Well, like what? I said, what's this building that you guys are designing? What does it have for cladding? Oh, it has HPL, high pressure laminate. Like phenolic, right? What's the vapor permeance of that? 0. So what do you have to worry about? You need to vent the crap out of that because you just made everything diffuse out to the back of that and it's going to condense. Okay, so your solution could work as long as it's got a really well ventilated cladding on the outside. Okay, so we're right. I'm like, well, let's think about a different scenario. What if I wasn't using the HPL cladding? What happens if I had limestone? And then the rain hits the limestone and it soaks in, and then the sun hits the limestone and it starts drying inbound. Now that water vapor goes straight through the vapor permeable insulation and straight through my vapor permeable air water barrier, and the next thing it hits is the wood, which is not that vapor permeable. And so now the sun-driven moisture becomes the source of the wetting. And so, if we had a air water vapor barrier and we had a vapor impermeable insulation, I could also use vapor permeable insulation, well, I don't care, then that air water vapor barrier protects the wood, right? And so the other half of the class said, okay, so we're the ones that are right. I'm like, what's the downside to what you're doing? It's got to start dry, and it's got to stay dry, its entire service. Both of these things can work, but depending on which thing you pick, there are certain things that you absolutely have to do and certain things that you cannot let happen. And so which answer is right? Neither one. And they're both right. You just have to be aware of what the decision, what the choice means for all the other issues. And so, if you go to our West Coast offices, they're hell-bent on vapor permeable. In our East Coast offices, we're like, yeah, you don't want petroleum products? Stone's good. Oh, I don't care. I just want lots of R value in a tiny space. Yeah. Polyiso's good. I'm happy with all of them. Just tell me what your parameters are, and we'll make sure that whatever direction you're going has got the best plan. So, is that helpful? Yeah. Cool. All right, thank you.